Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show. Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have J. Evan Ward, who's a professor and the head of marine sciences at University of Connecticut. We're going to talk about microplastics in the oceans and in shellfish. Professor Ward was awarded a PhD in marine biology and biochemistry from the University of Delaware in 1989. He's a recipient of the E. Sam Fitz Award for the greatest aptitude for professional development in marine studies as well. Again, he's a professor of marine sciences at UConn. He's also been the recipient of a National Science Foundation Career Award and 2 Fulbright foreign scholarships, which is excellent. Welcome today, Evan. Thank you for coming.
Well, thanks for having me, Richard, and good afternoon.
Yeah. Well, tell me a bit about your background and how you got to study microplastics and how they affect ocean creatures and the ocean itself.
Sure. So most of my career, I've been studying filter feeding marine invertebrates, and I focus mostly on commercially important species. So those are typically oysters and clams and mussels, scallops, things like that. So for many years, I studied basic feeding physiology and energetics in these animals. And probably about 15 years ago, I became interested in the issues with nanomaterials entering our waterways and our estuaries and our oceans. And from that, I became interested in microplastics as some of the issues with macroplastics, with marine debris and microplastics came to light. So it was a natural progression for me to go from studying nanomaterials to microplastics.
So where in the water column do microplastics tend to hang out? And is it different for salt water versus brackish versus freshwater?
To some degree, it really depends more on the polymer type. So there are some plastic polymers that are very light, like polystyrene, and they tend to float more on the surface. And there are others that are more dense, which tend to be found mid-water column. But because there's opportunities for conglomeration or aggregation of this material with natural materials in seawater and in freshwater, pretty much most of the particles over time will get bound up with these other materials and sink to the bottom. So the ultimate fate of most of this material is sinking through the water column to the benthos, to the bottom.
And on the bottom, I guess scallops, mussels, etc. You said they're filter feeders, so I guess they're creating a lot of negative pressure to suck in material, and in this way, some of these microplastics, along with other materials, get sucked into their, into their bodies and pass through them and get stuck.
Well, that's right. That's right. So these animals make a living at collecting natural particles, phytoplankton, small detrital particles, things like that from the water column, and they filter them out using their gills. And then they have a really neat process by which they move using what's called mucociliary processes, move that material to the mouth for ingestion. Now, although they can capture particles, it depends on the species, but they can capture particles down to a few micrometers in size, they don't ingest everything they capture. So most of the bivalves have the ability to select particles. So some of the material that is taken towards the mouth is spit out before it's ingested, and other material is ingested. So they do have the ability to select particles that they are capturing. So it'd be just like if I, gave you a spoonful of peas and carrots, right? Small peas and cut up carrots, and asked you then to use your tongue and, find the peas and spit them out and swallow the carrots. You'd be pretty good at that, right? You could probably not 80-90% of the time you'd be able to spit out the peas and swallow the carrots. So it's sort of the same thing. So they have all these small little particles that they capture, but they have the ability to spit out some of them before they ingest.
What is the local microenvironment like for the plastics? Less oxygen than at the surface, but probably not deep enough to be significantly less sunlight penetration, but again, probably not significantly deep enough where it maybe falls off a cliff. pH, salinity, what does this do to the microplastics that are bound up near the bottom of a body of water?
Yeah. So when fresh water counters salt water, there is an agglomeration of material due to changes in salinity. And you can see that actually when you're in estuaries. So a lot of this material, at least temporarily, accumulates on this boundary between the lighter fresh water and the heavier salt water as it moves out of the estuary or out of the estuarine rivers into bodies of water like Long Island Sound or some of the other bays that you have here on the East Coast. So certainly salinity does affect how the particles interact with natural materials, organic materials. So you have to realize there's a whole range of organic material, right? From truly dissolved organic material to what's called colloidal material, which is just on the one side of dissolved. So you have dissolved, colloidal, and then you have particulate material. So a lot of that can be organic. Some of it is inorganic as well, but most of it's organic material. So this dissolved and colloidal and particulate organic matter interact with those microplastics, which is, it's organic in nature, but it's refractory, man-made material, synthetic material. So there's a lot of interactions, and then those particles can interact with larger particles forming aggregations, and those aggregations tend to settle faster than if the material wasn't in aggregations. Oxygen really doesn't have too much of an effect on the aggregation and the way in which microplastics interact with the organic material. And what else did you say? You said salinity, oxygen, and temperature?
Yeah, pH, temperature, sunlight.
Yeah. Certainly those things, pH would affect the charge on the surface of the microplastic, but it also affects charge on inorganic material, natural inorganic material as well. So certainly all those things sort of mix together in a very complex manner to determine the fate of the microplastics. So whether those microplastics are going to be bound up with natural organic material, whether they're going to end up floating on the top of the water for a little bit, whether they're going to be taken right to the bottom and buried very quickly. So those things definitely affect the way in which microplastics interact with the environment and the ultimate fate. Well, I wouldn't say the ultimate fate. I would say the short-term fate of those particles, because the ultimate fate of most of the microplastic particles is going to be to the bottom. It just depends. Depending on these things that you outlined, it would take maybe a shorter amount of time or a longer amount of time to get to the bottom. Does that make sense?
I would think the plastics that sink the fastest would be the least perturbed, would have the least possible microplastic load. I don't know if they get And has anyone done sampling in the same water column at the surface, midway, and at the bottom, and looked at the stratification of the microplastics, how different it is in a given area?
Yeah, that has been done. We have done a little bit of that. We have taken samples from the water column, from the bottom, and from oysters that are on the bottom, and compare the types of microplastics and the concentrations. So the types of microplastics vary. Concentrations tend to be higher, a little higher in the bottom sediments than in the water column. Yeah, and people have done that. People have studied that. I don't have that right off the top of my head. Those are things we could look up. But yeah, there certainly are studies in which people are looking at, like you said, the water column and where in the water column these different microplastics can be found, at least on the short term.
Right. Okay. So of the creatures that you look at and, look for the microplastic load, what's the differences you see, a shrimp versus a clam versus a mussel, et cetera? Which ones seem to have the most disturbance from microplastics or affected most adversely?
Yeah. Well, that's a complex question because we really don't have very good information on the effects of microplastics at environmentally relevant concentrations on these animals. And that's a real important point that I want to drive home. And that is most of the studies that have been done using microplastic concentrations that are orders of magnitude higher than what we find in the environment. So these concentrations were used because toxicologists like to find a lethal dose or an effective dose 50. So where 50% of the population is affected or, dies from a particular pollutant. So in order to get that, you have to use very high concentrations of microplastics. So we know some of the LD or ED 50s, the effective dose 50s, but there's very little data on the effects of chronic low-level concentrations of microplastics. Because you have to realize, even though there's been a lot of publicity regarding microplastics, the concentration of microplastics in the water column is fairly low. It ranges from much, much less than 1 particle per liter. So a gallon, there's about 4 liters in a gallon. So let's just put it on a gallon basis. So much, much less than 1 particle per gallon to, some high, very polluted concentrations, maybe 40 particles per gallon, something like that. So that's not a lot, right? Very few. And to do experiments using those very low concentrations is difficult because it's hard to quantify the concentration that you're using in your experimental system. Try to find much, much less than 1 particle per liter in your experimental system.
Has anyone set up a tank and put some mussels in there, let's say a saltwater or freshwater tank, and, you started out with clean water and then you added up to a concentration, let's say of, 40, 50 particles per gallon and, let it run for a couple of weeks and see what the resulting concentration is. If you do histology on the mussels after, let's say, a month.
Yeah, there's been actually few studies done like that, but there was one published last year in which they used close to environmentally relevant concentrations. Actually, one of their treatments was environmentally relevant concentrations, and they let it run for, I forget exactly the amount of time, but it was like 8 or 9 months. So very long exposure time at very low concentrations. And they used mussels, I believe. And the bottom line was there was no effect.
There was no effect? What about the resulting concentration in the mussels?
So certainly if you set up a scenario like you said, and you put a mussel in an aquarium and put in microplastics, those microplastics will disappear from the water column. We know that. We know that bivalves in general can filter out the microplastics, just like they filter out all particles in the water column. Now, the key is, number one is, remember I told you bivalves can particle select. So they end up spitting out a lot of the microplastics depending on size and shape. So a lot of the microplastics don't go into the gut. They don't go into the animal proper, right? So they're spit out before they're ingested. Of the particles that end up being ingested, they egest or basically poop out the microplastics very quickly within sometimes an hour. So the result is that the number of microplastics in the animal is actually pretty low. So, and this would be if you gave them hundreds or thousands of microplastics per liter, which is much higher than environmentally relevant concentration, the good news story for bivalves is that they spit out a lot of the microplastics. And of the microplastics that they do ingest, a lot of those are egested, pooped out very quickly. So yeah, you can find microplastics in bivalves, and we've done many studies on that. But if you look in a natural environment, the concentration in the animal is anywhere from 0, no microplastics, to like 4 microplastics per animal. So
if I'm a mussel and I'm hanging out at the bottom of the ocean or something, I would think, look, as I filter and poop out, get rid of the microplastics around me, they would slowly build up more and more and more in my local environments. And I'm just guessing, would it make it harder? Would it make my job harder where like you said, the peas and carrots example. So what if I started getting 50% peas, then 60, then 80, then 95% peas, and I'm spending most of my time spitting those things out, and I'm getting less and less food? Maybe do the microplastics build up and act as an exclusionary item that makes it harder to feed?
Yeah, so that's a good point. So first, let's remember that the concentration of microplastics in the water column is very low right now. Now, maybe 100 years from now, that would be an issue. But right now, the number of microplastics, let's say there's even 10 microplastics per liter, which would be very high. There are thousands, tens of thousands of natural particles per liter, just to give you a perspective, right? So again, the number of microplastics that these animals are encountering on a per day basis pales in comparison to the amount of natural particles that they're processing each day. So yeah, on the bottom, you do find higher concentrations, and over time, those bottom concentrations are going to increase, but the microplastics are not the only thing settling to the bottom, right? There's a lot of silt and detrital material, etc. So these microplastics get buried as well. So for bivalves, most bivalves, which are suspension feeders, there are some bivalves that feed on silt that's deposited, but very few. So for bivalves that are really filtering the water column, the issue is less problematic. Now, over time, you are right. The microplastics are accumulating on the bottom. So if you're a deposit feeding worm, you're getting, and you will get over time, more and more microplastics as they settle to the bottom. Because once they settle to the bottom, they're really not going anywhere. Sure, there might be resuspension events, a storm event or something, but if we discount that, because they're rare events, the microplastics are staying in the bottom and they're buried by silt, etc. And as we know, the microplastics take a long time to break down. Those synthetic polymers take a long time to break down. So they're going to be in the bottom material for quite some time.
Yeah. Well, what about in a shallow area where your wave action maybe disturbs the bottom enough to freshen it or keep it from accumulating?
Yeah, sure.
Versus deeper, quieter bodies of water where it doesn't.
Right. So you would suspect that more of the microplastics might get resuspended per time. But when you take samples from even shallow water, I mean, we worked in areas that were like 15 feet deep. That's pretty shallow. You really don't see a large increase in microplastics, right, per liter. And the reason is because it's very low, right? I mean, you think that around here in Long Island Sound, off our docks, it's just a few particles per liter. And so if there's a resuspension event, and again, it's going to be diluted because there's a lot of liters of water. Let's say it goes from 2 particles per liter, right? And you double that during a resuspension event, it's still 4 particles per liter, right? It still, again, pales in comparison to the amount of natural particles per liter that are in the water column.
Yeah. What about the provenance of the microplastics? Do you see more fibers? Like what's predominantly in the water, if anything?
Yeah, so mostly fibers. Fibers are found quite often. And after fibers are fragments. So fragments come, and it depends where you are. So when we're sampling off the docks here at Avery Point campus, you see a lot of fragments, and a good portion of those fragments are paint fragments, which are basically synthetic materials. But you do see a lot of fibers as well. Fibers are coming from a variety of sources, from ropes, right? Think about all the synthetic ropes that all the boats use all around, right? They fray, and those get into the water column. From our clothing, right? Most of the clothing we wear is synthetic. So when you're washing your clothes, some of that goes down the drain and goes to sewage treatment plants. But the sewage treatment plant isn't 100% effective at getting those out. So then that gets into rivers and into estuaries and comes down. So yeah, fibers are seen quite often in our samples and in the samples of other people that have done this work.
Okay. So what kind of, creatures and bodies of water seem to be the most susceptible? Is it just, fish that kind of live mid-column in the water? Or, does it affect phytoplankton that may be on the surface? What are most affected?
Yeah. So we can talk about what's the most effective, but let's change our scale, because I think when we change our scale, we will get a better feeling for what are most effective. So where do microplastics come from? I sort of hinted at it earlier, but a lot of microplastics come from the breakdown of macroplastics. Pieces of rope, fragments come from paint chipping off, or from bottles that are floating in the ocean. They crumble and they crack and they produce small pieces of plastic, maybe, an inch in size and then a half inch and a quarter inch, and away we go down the spectrum. So those macroplastics probably have the most profound effect. And I'm sure most of your listeners have seen pictures of birds, right, with macroplastics in their gut, fishes with macroplastics in their gut, charismatic megafauna, turtles eating plastic bags, marine mammals with entangled plastic materials, right? We've all seen pictures of that. So those are well documented effects of plastic, large pieces of plastic, but nonetheless, plastic on marine organisms. As you start moving down the size of the plastics, I would say filter feeding fishes and maybe some filter feeding crustaceans such as shrimp and things like that would be affected, because the pieces of plastic are big enough that it can clog their intestine and cause harm. As the plastic material gets smaller and smaller, now we're down to the microplastics like we talked about before, the effects are harder to see. And the reason is because, as I said previously, is the concentration becomes lower and lower. And so you just don't see that yet, right? You don't see many effects at environmentally relevant concentrations. Again, maybe 100 years from now, it's going to be a different story. 200 years from now, if we don't clean up the macroplastics. So most of the microplastics are coming from the macroplastics. Bottles, they get, so go ahead.
How much of the digestion process of various animals changes, plastics to microplastics? Like if, the creature eats a piece of plastic and there won't be zero digestion, there'll be a little bit, but what does it do to the plastic? Like how much is the digestion of all the creatures in the sea affecting the microplastic load? Is it increasing it? Not substantially? Can anyone tell?
Yeah. I just read a paper, as a matter of fact, that looked at the fragmentation of macroplastics by, I think it was seabirds maybe, or it was a fish. I can't recall right off the top of my head, but right, there is some documentation that the process of going through a gut increases the fragmentation of the particles. So that is something that is occurring. How important that is worldwide, I'm not sure. Certainly mechanical fragmentation is very important, and weakening of the plastics through UV contact, right? So you're probably familiar with, you're walking along a beach or a sidewalk or something like that, and there's an old plastic bottle, and you step on it, you hear that crunch, right? That's because the ultraviolet rays have weakened that plastic, the bonds in the plastic. So then when you step on it, it fractures. And you hear that crunch, and maybe sometimes you even see a little puff of, fine material, and that's microplastics. So that's really important. And then mechanical abrasion. So the act of those plastic and many times UV degraded plastics going over a waterfall, getting broken up by wave action, or those types of things. Those mechanical breakdowns are very important too. But without a doubt, there is some biological fragmentation occurring as well. How much of that is and how that compares to the other types of fragmentation, I don't think is really well known at this point in time.
I was going to ask for different types of plastic in bodies of water. Has anyone looked at the fragmentation rate and ratio? So if I, throw a plastic bottle and it's bobbing along in a body of water and starts breaking down, will it create like quadrillions of microplastics? Is there an extrapolation to be made? Based on your comments, it seems like getting rid of the macroplastics is incredibly important, because I would guess that each macroplastic could degrade into, again, quintillions of microplastics.
Yeah, right. So interesting. I was just talking to the other week a colleague of mine at the EPA, and there is an estimate that one water bottle, let's say 1 liter water bottle, when it fully degrades, can produce 10 to the 19th 100 micrometer particles. So 10 with 19 zeros next to it from one liter bottle. Now, of course, that's an estimate, but that's a lot of microplastics from one liter plastic bottle. And yeah, they're entering the ocean. And that's why I said that right now the concentration is pretty low. But what's going to happen in 100 years from now, 200 years from now, if we don't get all this plastic out of the oceans and stop it from getting in? That's the issue right now, is that there's a steady stream of plastics that enter every year. The latest estimate was anywhere between 500 and 8,000 kilotons of plastic enter the oceans each year. That's a lot. I mean, that's a big spread.
That's great.
Because the model, it depends on which model you look at, but let's even take the lower end. 500 kilotons of plastic enter the oceans each year. And it's estimated in this year, 2023, anywhere between 11 to 110 million metric tons are in the oceans.
Do you think that this is understood? Is there consensus or any strong viewpoints that, all right, we need to remove as many macroplastics as we can from bodies of water before they cause, downstream orders of magnitude more microplastic load? It seems like this is the linchpin.
Yeah.
To get rid of these macroplastics as fast as possible.
Yeah, absolutely. And NOAA has a whole program on marine debris removal. So they fund groups to go out and remove marine debris. Most of it's plastic. A lot of it comes from derelict fishing gear. A lot of it comes from just the mismanaged waste of bottles and bags and all that kind of stuff. There's also some NGOs that are looking at removing plastic materials from the ocean. So there's one, I think it's Clean Ocean Cleanup. I'd have to get the exact name, but they have a system out in probably heard the Great Pacific Garbage Patch in the Pacific Ocean, where they have boom networks where they put these booms out there and basically propel them through the water to catch as much macroplastic as they can. So certainly there are NGOs and government agencies that are well aware of this and trying to go out and remove the plastics from the ocean. But if you think about it, that's good to do, fine. But the important thing is we've got to turn off the supply, right? So I was at a conference last year, and one of the people that was speaking with me said, well, if you walked into your kitchen and you saw that the water was running into your sink and the sink was overflowing, what would you do first? Would you grab a mop and start, getting the water off the floor, or would you go and turn the tap off? I think we know what the answer is. You go and turn the tap off first before you get your mop, right?
Right.
So right now, all we're doing is we're mopping the floor, but we're not turning the tap off. So we got to get the tap turned off first. Then we can mop the floor and try to remove some of this marine debris and these macroplastics from the oceans.
But remember, too, it's not one person with an overflowing sink. There's many, many, many groups.
Oh, yeah.
Would it not be better to focus on multiple angles at once instead of just saying, well, yeah, we should get rid of the macroplastics, but we got to stop putting them in the first place? That's certainly not going to happen anywhere close to overnight, and there's all kinds of trade-offs with that.
Yeah.
So why not pick 3 or 4 major contributors and attack them all at once to really make things work?
Yeah, right. So that gets to where most of the plastic waste is entering our oceans, and most of it is occurring around Asia. Okay, so certainly U.S. contributes, Europe, etc. But if you look at the hot spots, it's in the area of Asia. That's where a lot of the plastics are coming from. And you say, okay, well, we got to clean up they've got to get their act together and clean up their mess. But if you look at where most of the plastics are produced and exported to these areas, Indonesia and Asia, it's coming from Europe and the United States. So basically what we're doing is we're packaging our material in plastics, sending it over to these countries that have very little, if any, infrastructure in dealing with this material, and then sort of, patting ourselves on the back that we don't contribute much to the macroplastic problem in the oceans. We actually do indirectly. So that's number one, right? So we've got to hold the industry accountable for their product. And that means not just the product that's someone's consuming, but the product packaging. So that's definitely number one. We've got to hold them accountable. Number two is you're right, is that even in a perfect world, you're not going to get everyone to put their plastics in the right receptacle, right? So the next step is we've got to start working on more truly biodegradable plastics. And there's a number of companies that have come up with some very good biodegradable plastics. We were working with a company in Italy called Novamont that makes a film, a plastic-like film that biodegrades very quickly. So, and they're not the only company. So that's another step, right? Is to say, okay, we're going to stop using all of these synthetic polymers that we know don't degrade, and we're going to start transitioning into these plastic films that degrade over a period of months to, a year or something like that. And then the third thing is to find ways to better recycle plastics. And that's not only chemical, but biochemical. So working to find bacteria that can truly degrade synthetic polymers that we have, and work with the manufacturers and with the recyclable companies, the companies that recycle materials, to create chemistry that is more easily broken down and recycled. Because right now, some of the plastic that is sold is very resistant to recycling because of the chemical nature of it. So, there's just three places that we could do a lot better.
Well, also looking at bodies of water that empty into larger bodies of water, the ocean, and, if there are choke points that could be monitored and filtered more actively, that may be another way to help.
Yeah, right. And in some of the developing countries that we just talked about, they actually have basically what looks like storm drain gates that are mounted vertically instead of horizontally that trap plastics as the river's flowing. So, right, that is another strategy. Of course, there's some downsides to that because you don't want to restrict the movement of fish and, other organisms that are using the waterways to move around. But yes, that's another way, right? And in some small rivers, you can do that. Something like the Connecticut River, you can't do that. The Mississippi River, you wouldn't be able to do that in the Mississippi River, right? But certainly all of these things we have to start thinking about and trying, right, to remove these macroplastics, because that's the real problem, is the macroplastics.
Yeah, last question also, too, is there a trade-off when plastic is recycled? Is it then more friable? Is it less likely to break down? Is it more likely to break down? Is it, again, are there trade-offs in the recycling plastic? It looks like it would be a good, virtuous thing, but what if it creates plastics that make even more microplastics faster, let's say?
Yeah, I don't know the answer to that one. You've stumped me on that one. I'm not a chemist, so I don't know the answer to that. I know, as I said before, I know that there are many plastics that are difficult to recycle because of their chemical nature, and that there are groups working on changing that chemistry so that those plastics are more easily recycled. But yeah, I don't really know the answer to that question. And certainly something that you alluded to earlier, I didn't really address, at least I think you alluded to it. Certainly plastics have made our life better, without a doubt, right? They make our food safer. They make our cars lighter and more energy efficient. They have helped in the medical industry immensely. So it's not plastics per se. It's how we manage the plastic and how we deal with the plastic, because plastics aren't going away, and they've really helped our society immensely. But we just have to do a better job managing the plastics.
Well, very good, Evan. We're out of time. What's the best place for people to find out more about your work? Where can they go?
So they can go to the UConn website and just Google my name, or they could just go to the World Wide Web and Google my name and marine after it. So if you Google my name, J. Evan Ward, marine, you will undoubtedly find my website.
Excellent. Well, Evan, thank you so much for coming on the podcast. It was a really good conversation. I appreciate it.
Yeah, very, very good conversation there, Richard, and thank you for having me. It was a pleasure.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.